Again, good afternoon. This afternoon, we have the pleasure of welcoming Professor Ludger Overbeck from the Justus-Liebig University in Giessen. Ja, herzlich willkommen. Yeah. Professor Overbeck studied probability theory and has a PhD from the university, sorry, I don't remember, Bonn. Frankfurt was the habilitation in economics, yeah? And he also has a habilitation in applied mathematics from the same university or in Bonn. Yeah, he worked for a while as a professional banker, yeah, for the German Bundesbank, yeah, this probably a central bank in Germany, yeah. And in 2003, he joined the University of in Giessen, yeah. But I think he's still consulting for many central banks, the World Bank, and other commercial banks. And he's also co-authored a very famous book on credit risk modeling, yeah, that has lots of citations. I checked. Yeah. So, and today he will speak about some of his more recent work on, I don't know, stochastic analysis and surroundings, we probably could call it. Yeah. So, Professor Overbeck, thank you very much for joining us. We are very looking forward to your presentation.
Okay. Many thanks for a very kind introduction and for the warm welcome, even hot welcome to Stellenbosch, coming out of a freezing area, an increase in temperature by 40 degrees. Because it's skiing season, you know, in Europe. I went skiing last week. It's an increase of 40 degrees Celsius in a few days. Yes. I always worked on stochastic processes. Yeah? So I'm a mathematician, so I'm in the mathematics department. So of course you need these nice posters here. Guess which of the two posters I like more? This one or this one? Which one? No, I like more this one, yeah, because mathematics is in the middle. Yeah? Yeah? All people doing quantitative research, they use mathematics as a language. Yeah? Only mathematicians, they don't use mathematics as a language, they develop language. Yeah? Just to make advertise mathematics, because I don't know how it's in your country. In my country, nobody wants to study mathematics anymore. Okay. But of course, mathematics is important because it's so many applications. Yeah? Yeah, as you've seen, I have started actually to work in quantitative biology. No? And I will explain it in one of the equations. Equations coming in quantitative biology are also used like in quantitative finance. Also, all this was here, like Bayesian methods, of course, are applied. Any case of any instance of statistics, stochastic process with hidden states, also independent or not independent from the application. Of course, it's always motivated by application, and specific questions, of course, are motivated by applications. Okay. That's the structure of my talk. I will give probably not so much details. Of course, it always depends what you mean by details. So let me start with a problem formulation. So basically, Markov switching models were introduced to assess latent states of a system. For example, and that's the final application which I currently follow most of the time, is in the economy or markets, where the market has regimes like expansion and contraction. There might be good times and bad times, and they might change according to a Markovian law. That's the Markov switching means the switching of the state is also as a Markov property. And once you have specified your regime at each time, you then have evolution, like a price evolution, or like in biology, the evolution of the genes or the evolution of the population or whatever. And as you will see later, we will concentrate on the so-called subclass of Levy process with a stochastic process, which are quite general, basically the independent increment that the more or less defining property. This means the increase over time interval doesn't depend the level you are on it, just a percentage increase. Okay, and if you have the Levy process, let's say like Brownian motion, perhaps you know you have described it more or less by a drift and a volatility or standard deviation. Of course, it's always what's called sigma. In the area where you work, it might be volatility, standard deviation, whatever, a name for this. But it's always mathematically the diffusion coefficient of an equation. This might change according to some underlying Markov. Levy process has more parameters, we will see later, but the basic idea of this paper, of this project, is done for Brownian motion in a preprint by Ayer and others. Just in order not to forget it. This is joint work. This is still work in progress with my colleagues Anindya Goswami from IISER Pune in India, and our joint PhD student who's now at Warwick University, Tridash. You see, Anindya and myself, we are mathematicians. Our student is a data scientist. But we do the same, just under different names. Okay. And then to estimate the parameter, we apply Bayesian inference. Bayesian inference, like you probably know from standard statistics, you want to estimate a parameter like the mean of a normal distribution. You just take data and you take the empirical mean as estimator. Like Bayesian is different. Also, your parameter is random. You are not certain about the parameter. So the parameter is a random variable and assume some prior knowledge on the parameter. Let's say parameter itself has normal distribution around the parameter you think is the best estimate. That's your, let's say, data-free assumption, or the best you would guess today without seeing new data. And then you see new data and you update your knowledge or your opinion about the distribution of the parameter. And we will see it in a simple example, but this can be applied to these more complex models as well. And then, of course, because you have calculated posterior distribution, meaning the new distribution of the parameter after you have learned from new data, what will be the new distribution parameter? Once you started with randomness, you will never get rid of it. You try to understand randomness better, but it's still the uncertainty is on a different level. Okay, and the process we are considering, let's start with the even more general one. So that's a typical description for all of you don't like probability. They just erase the second part. You have just the ordinary differential equation. In S is a function of t, and the change in d probability, you call this a drift, is driven by a function of your current state. You are considering, let's say, prices, asset, and in addition of some underlying random process, which is the Markov chain. And as we are in finance, you're mainly concerned with this one, the volatility. As I told you in the introduction, volatility might take different values. Let's say you have two states, xt equals 1. You are in expansion, xt equals 2. You are in contraction. And of course, it might then still depend on the current state. But the functional relation is also a function of the underlying state, and the same for the driving noise. Okay, this is our Levy process, so to say, but of course, let's say for presentation purpose, let's say that's a Brownian motion. Okay, we were actually motivated by this equation. That's a typical, you can say that's what's called a kind of a mean reversion. Mean, that's if you say the deterministic part, let's say this would be not dependent on xt, that's a fixed parameter eta and a fixed parameter kappa. So as a deterministic equation, this would always fluctuate around the mean reversion level. It always returns to the mean, like a logistic equation, and this is the speed of mean reversion. And so because the advantage of this one, or you use it when st is positive one, like in interest rate, very different from like equities. Different rates shouldn't go to infinity, put it like this. They should always be somewhere bounded, going back to a kind of long-range interest rate with some speed. So this type of drift is quite often used in interest rate modeling. And then you have the volatility term, again, might depend on the state and the parameters of this one. Okay, what's our estimation problem? So we just observe that, well, it's hidden. We just observe the prices, let's say, or the interest rate at discrete time points from 1 to capital T. And we don't observe the underlying Markov chain because nobody tells us in which regime we are. And so taking values in M states, M potential state from the underlying variables. And this means in each of the states, we have a different long-term mean, we have a different mean reversion, we have a different volatility, and they also fluctuate. In the Bayesian world with the data, they also are random because these are the parameters. So if we just do standard statistics, we have still a high-dimensional parameter space. In the dimension of k, eta, and this, in our case, they are all one-dimensional, and theta might be of larger dimension. And we have each state, we have to estimate as well, even if we don't know in which state these are, still we have to estimate the value in this state as well. No, we don't know the states and we don't know the parameter state. And so this led to the challenge of this research project is, okay, we might view the underlying path, if you like, also as a parameter. If we would know the underlying path, we should just estimate this as standard parameters. This means one output of this method is always the path which fits best to the observed data. Okay, let me give some very subjective review of the literature. So regime switching is also used like in that's a kind Hamilton is one in time series analysis. That's why I think it started more or less in time series analysis or econometrics by Hamilton and his co-authors, and then the numerous paper in this area of discrete time stochastic process. I would say as a mathematician, the economists say econometrics. And so this was my first question in regime switching, that's in the pricing area, how to price an option if you have like a regime shifted in a Cox-Ingersoll-Ross. And so you see when I work with my collaborators from Pune in India, first paper on this. And then you see a very important paper, because it was my first project with somebody from NITheCS, namely with Matthias. So we did this paper, regime switching rough Heston model. So I started more, I came because of regime switching, and Matthias had this rough idea, a very rough idea, which was very good. So we still are working on rough models even, I don't know how many years later, we started in 2017, still the rough part is still a mathematical challenge. I don't go into this during this talk. And the Bayesian estimation, that's something we start now to do for this purpose. We more or less use these two papers. That's the one by Ishwaran and Saripur. We use techniques from this, what we call Dirichlet distribution. I come back to this. That's the distribution on the path, base of the path of the underlying Markov process. Some people call it non-parametric statistics, but of course, it's just a question of definition. And as I said, so this is done in a simpler approach by these three authors where we also benefit a lot from. Okay, let me now explain Bayesian inference in a little bit more detail. So we have a parameter of interest. Nowadays, it's actually high dimensional. You know, also this Bayesian estimation also become fashionable again, because also in artificial intelligence, you have many Bayesian methods, probably with more sexy names than just Bayesian statistics. They call it probably much, the terminology is much more attracting, put it like this. Okay. This might be high dimensional space, like in neural networks. I think I wrote it down how many parameters ChatGPT has. I think it's 2.5 billion parameters. Yeah, like ChatGPT, which is a big prediction engine, I think has parameter space. So the parameter space, this capital Xi, might be of dimension billions. Okay, and once we know this parameter, once we have trained ChatGPT, it will tell you the next word, which is also random. That's the modern prediction engine, but in any other statistical problem, of course, that's the perception of a statistician towards the artificial intelligence. So classically, you just say, okay, once you know the parameter, you know the distribution. Noted by this density, notation to make F index is always, you get the distribution of random variable x at value x given the parameter at the time theta. Okay, this, and in addition, as I said, we have also the distribution of the parameter. That's the Bayesian approach. That the parameter itself is random. Or put like this, unknown. It's unknown. And so the philosophical assumption of the Bayesian is not unknown, because we just don't know it. It's a random variable. And then we have the joint distribution of the parameter and of the data. And this gives us the connection. If we know the distribution of theta, we know this density, the conditional density or likelihood of the data given the parameter, and altogether we infer, once we observe data, we can infer what's the distribution of our new parameter. We update our assumptions so far on the parameter by looking at data. This formula tells you, when you have data, you will change your opinion about the distribution of the parameter. And that's not an opinion, that's a rule how you change it. Okay, and then you have this calculation here. These two we more or less know from all this here, from our assumption here. And so we get the posterior distribution. We plug in here our new observed data. We get a new distribution. And if you still want to have one value of this, for example, you take the mode of the posterior distribution. It's called the maximum a posteriori estimator. You have a distribution, and you take the peak of this, of the density, to you substitute for a deterministic. Classical frequentist, you want to have one number, and then the Bayesian talks to a frequentist, as the others are told. You just say, okay, just take this one. And all the computational problem, at least in this case we have, is of course, you have data, but in particular you have a high dimensional complex parameter space. And you want to sample from this, and this we do by a Markov Chain Monte Carlo method to do this. An example. Okay, as I said, we assume that our data are normal distribution, or we just assume that we have a known sigma here. The only parameter we want to estimate is the mean. Okay, so the density is just a normal, or the likelihood function is a normal density. And then we assume, okay, we actually don't know the parameter, but we think, again, the parameter is distributed, and to make it simple, it's again a normal distribution around our best estimate we would have so far, and we would believe, okay, this is random, we don't know exactly, so we again say Yeah? It's a normal distribution around our, let's say, belief. But the belief is not a knowledge, it's just a belief which is uncertain. Okay. And this means everything what we have on the previous slide is now given explicitly in terms of normal distribution. Okay, then we'll have our new data coming in and new points. Let's say that's what we want to consider in insurance, because here's the insurance department, on a lifetime of human being. The average life expectation, you think, okay, to my current tables, it's like 70, but you know, this change over time, this might be uncertain. So my estimation for the lifetime, average lifetime of human is a normal distribution around 70 years with some standard deviation plus minus 10 years. And then, unfortunately, that's consequence of life. You have some new debts, and you see, get some new information on your life expected. And so if this would have a fixed parameter here, it's just a product of normal distribution because you think they all die independently. It's a lot of mathematical assumption, of course, behind this. Then you do this calculation, and then you see that the new, that's the nice thing about normal, they are what's called conjugate. So if you start with a normal and you assume normality, you get normality. That's another advantage of normal distribution. Stay in the same class, which is not necessarily for others. That conditional distributions are also normal. Okay, what you see, your new parameter after observing, let's say, 10 new lifetimes. It's again a normal distribution. It has now a volatility, a standard deviation which depends on n. It has a new mean. This is updated from your theta 0 in the following sense, and that's quite illustrative. Okay, this you would take as a frequent test. You don't care and say, okay, from my 10 new deaths, the average is 75, so my new one is 75. Of course, not true because you have prior knowledge, however, or belief. So this means your new mean is a mixture of the empirical mean of your data plus your old belief, and they are weighted by the inverse of the volatility. This means if you are very sure about your belief, this has high influence. If your data and your assumption have a small variability, that's 75 or 75.1, 75.2, and 3, it has a very small volatility, or your assumption on this one, then this is more important. You see this Bayesian estimation gives you a mixture of your belief and of your new data, and they're weighted according to the certainty about your belief or the certainty about the data. If you translate 1 over variance as certainty. So I think it looks like a useful concept. So we also want to apply it to our model. To give you a simple example of this mixture model, again, we with normal distribution. You assume your data are normal in 2 regimes. So, and the regime 1 has probability 0, so the regime 2, nothing is left, has probability 1 minus p0. So you have a mixture of normal densities. In this case, it can given be explicitly the one. Actually, that's a model which is used by large banks for the risk management. Like large bank or some large banks, they use this actually the concept of hectic and non-hectic volatility, as they call it. They have some opinion that the hectic volatility appears with a 10%. Actually, if you believe in the Bible, every 7 years. And average, you have the other 6 years. Bad times comes every 7 years, or whatever you estimate here. And then you have something, let's say, with a low volatility and others with a high volatility. Okay, and this you can make, to make it clear, more states, then you have a formula like this. Basically, these mixing models are straightforward in this setting. Yeah? So we are similar here. Yes, and I said these are models for the prediction of your profit and loss distribution, let's say 1 year ahead. Okay, now we come to the question in our case, how to sample from the posterior distribution. We have, let's say, a high dimensional space psi for your parameter space theta. So you have observed data, yeah, and you get a new distribution. This was which came from Bayes theory. Given the data, what is a new distribution, which is called the posteriori distribution, so after observing the data. Yeah? So that's a very complex one. In this case, I just omit. We applied later for fixed data. Yeah? We have fixed data, so our F index theta actually depends on your observed data. Yeah? But just to make it clear, any complex distribution can be simulated by a Markov Chain Monte Carlo method. In the following sense, if again you know the conditional distribution, let's say theta, as I told you, D in ChatGPT is 2 billion. So you just sample one-dimensional distribution given all the marginals, and this step by step. So let's say in ChatGPT, after 2 billion steps, you have sampled each single parameter, which sounds a lot. That's why nobody did it before computers were invented or fast computers. But of course, you know it, before how it works. And then if you run through these samples, let's say 2 billion times, and you run 1 million times 2 billion times, then you became stationary. And the stationary distribution of this Markov chain, so each block of 2 billion parameter size, gives you the distribution, this complex distribution. This explained here. Keep sampling constructed part of a Markov chain on your state space. In our case, it's a state of parameters, and I call it theta. With each step given by this marginal distribution. This conditional distributions. You sample first your first parameter, taking your old parameters, and in each step you replace one parameter more of your 2 billion parameters in ChatGPT. And at the end, you see here the index now gone. So this value is ChatGPT dimension 2 billion. After 2 billion steps of the Markov chain, you get one new realization of your parameter. It's not yet the stationary distribution. Let's say you start with something with the second step and so on. And the invariant distribution, then you have to wait for the freezing of your distribution on this large space. You get a sample of length n from this distribution. Let's say after 1 million, you get the first. After 1 million of 2 million, 2 billion, you get the first realization. Then you have to do another one, and then you produce n samples which are close to the distribution you're looking. It's a high, again, complex, not a complex, a high dimensional calculation. Okay, and we apply this one, in our case, to the distribution of our parameter given the observation. And theta, my notation, theta is a random variable on space psi. And so we have now to look at this psi. And as I explained before, the psi is you have for each state, in our case, let's be a one-dimensional process, mean reversion, mean level, volatility in each of the states. Let's say we have m, 2. And then we have a parameter on the driving noise. Okay, For Brownian motion, we don't have this, but for Levy process, we have also another 2 parameters in the example you will see, which is dimension. This is dimension 2. So that is the state space of the real valued parameters once we know at which time we had which state. Okay, in addition, we have to consider the underlying Markov chain X. Okay, you can either say, okay, the parameter determines the distribution of the Markov chain. Let's use a transition matrix P. This would be very nice. Then we had a high, in this case, it's still the transition matrix Pij tells you the probability to step from state 1 to step j. It's a matrix dimension m squared. This we don't consider yet. We are a little bit lazy. We just produce a large number of Markov chains, of paths of a Markov chain. So our actually we take a finite but large sample out of this space. And then we consider this as each of these paths we consider as a class. I will explain this later. So we have, let's say, different steps. One is we just make it quite traditional, just an additional large dimensional parameter. We can say, okay, the parameter is a path. Then we take pi as our prior distribution on the path. And the next simplification is just in order not to take all paths, we start with a large number of once random, but then fixed paths, and you view it as classes and look at the best class we will have. And that's how you produce path, because on path space, you have to find a distribution, a random distribution on path space. So that's what's called the Dirichlet process. Okay, so in general, Dirichlet process, it's a kind of a random point measure with measures on space H, on state S. So it's a countable menu. So from some abstract space S, you sample according to this random measure. This means you randomly, they're all independent, you random choose keep infinitely many points, and each of them gets a random weight. So it's a random point measure. And so in order to have this a random point measure, this must sum up to 1. And so that's what you know in this area. You call this like, you take a stick of length 1 and break it into beta length parts. We have a beta distribution, the length has a beta distribution. That's more or less a standard way of sampling on a on discrete measures on a countable space. Count with many points. So for as I said, so we simplify so far all this one. So we take a large number. These are not states. These are paths of states. So each xy gives you, let's say, time 1 we are in state 1, time 2 in state 4, time 3, and so on. This is an entire path of states. And this is another one. And this we somehow choose the most random one. So the Markov chain behind this. We just say, okay, we start uniform. And if we are in state 1, we choose all other states with the same probability. So let's say uniform distribution on this path, if you like. And so this path we keep fixed so far. And consider them as classes and apply updating weights. And so that's what we got from this paper. How you, we say we have capital N classes, and now we want to find the best class fitting to the data. That's a Bayesian estimation. That's the standard approach, which we extended here slightly. Okay. And so this somehow, if you like, kind of the innovation to sample also in the Gibbs sampler also to use the path. And then once given the path, yeah, we still choose random. Oh, now I'm getting lost totally. Yeah, no. Ah, that's. I want to go backwards. Okay, we stayed here. Yeah? Okay. Now so we have n path, and the only thing we will change is are the weights. And later we take, of course, the path with the largest weight. By our data, only the weights pi are updated. Yeah, in the Gibbs sampler step, we therefore only update the weights as well and choose a new path. Yeah? But it's one out of this capital N path. Yeah? And given the new path, we sample the values of the parameters in the state at the time points. Now we know that at time 1 we have class 1, we have state 1, at time 2 we have state 5, and so on. We have the sequence of states through time. So we now have to sample what will be the parameters in each of the states. Yeah? Let's say if we want to know the parameter at underlying state 2, we take all time points into consideration where the underlying Markov chain was in state path of the Markov chain was in state 2. This we see it somewhere in the formulas. Okay, and so we use I don't go so much in the technical details here, but now we think now we have a kind what we now have. As we know it from regime switching, we have now a time inhomogeneous price evolution, because each time we have a different state, we have a different parameter. It's not a homogeneous process anymore. You have to keep track at which time you are in which state, whether you're hectic, whether you have 3 hectic times in the row and then 7 quiet times or whatever, you're switching all the time. Of course, this matters. It not matters how many you are, but also when. So it's inhomogeneous. Okay, this was the general approach of this Gibbs stuff for this stochastic processes. Now we specify the underlying stochastic process. As I said, Levy process are defined in this, let's say, abstract way. Yt is some random evolution in time, and the increments. So I am now at time t, and I want to know the increase up to tomorrow. It doesn't depend what happened before. The increments are independent. Yeah, so like in equities. Of course, if I'm now what's your favorite equity? I don't know. It used to be Tesla, but this has changed, of course. Okay, let's say Deutsche Bank. Yeah? Oh, yeah, Deutsche Bank is also bad because they were only financing of Trump. In NVIDIA. Okay. Okay. So you take like if your equity is already, let's say, worth $1,000, of course, this probability very low, it will be $100. But the percentage change to increase by 10% doesn't depend on the level. Whether you increase from 1,000 to 1,100 or from 100 to 110 should be the same. So in equities, you first have the increments, the changes, and they are stationary. You will see it later when we see the Okay. So usually from time series, somebody from econometrics here, like the first differences are usually stationary, not the process itself. Okay. And they are also an independent and stationary. It doesn't depend on just on whether you wait for 1 day or for 2 days, not which date you do it. And you have this technical assumption that this have this stochastic continuity. The Levy process and Levy process are characterized by the characteristics. Surprise, surprise. I don't write down what the characteristic is. I just give one example. Because then you know also the density, the normal inverse Gaussian process. has stationary increments. Basically, you know, you only have to specify y1. Huh? It's defined by one distribution. Huh? Okay, that's kind of this exponential stuff. And so, I mean, special handbook of mathematical functions in theoretical physics. That's kind of a Bessel function. It looks ugly, yeah, but actually it's less ugly than the normal distribution. Because the normal distribution is basically only given by integral, and here you have time series, which are sometimes even numerically more efficient. But you are just not used to it. Normal distribution is nice because you are used to it. Okay, so our first model, as I said, it takes the ST, the exponential, so this means the log of the price is stationary. First difference is in continuous time, it's just like the log. And so the set of parameters we are looking at, so we let alpha and beta, which we have seen before, fixed, because this gives you a convolution semigroup again. If you have fixed alpha beta, if you sum two different ones with M1 and delta 1, you get again a distribution in the same class. You can imagine this we need to run through time, that we are staying in the same class distributions. Okay, and then we have many prior distributions defined here. And see, for example, the mu, which is also C, the mu itself, it has a normal distribution. For in each state, they have the same. And only the algorithm will tell us, so the posterior distribution will be different in different states. The same for the delta, which is kind of a positive parameter, the half normal distribution, and so on. That's our beliefs at before, as we said, okay, our lifetime expectation is 70 years, plus a volatility of 10% about the 70 years. Here we have the same, we have some starting parameters. Unfortunately, it's called theta, of course, it's nothing to do with the entire theta. It's the mean of the mean, and the mean is a normal distribution with this parameter, with this volatility. We first have to formulate all our beliefs, which are in many cases just driven by technical issues, that you relatively easy get the posterior. And there are constraints, it will be positive and whatever, like let's say stylized effects. And here it's again in more detail what I said in words, that you truncate it directly prior on path space of the Markov chain, discrete time Markov chain. Of course, we also did it for continuous time Markov chain. And as I said, it's a uniform distribution. We start our starting distribution has equally starting points in our M, and the transition also has equal probability to go in all other states. And so we generate this number. You see prior distribution Gi, and then we have all this distribution. And then we look at the log returns. And we can calculate from all this, but by Bayes theory, more or less, we calculate. And that's the advantage of this Gibbs sampler, as many other Markov Chain Monte Carlo methods. This just means that you don't need to know what's in Bayes theorem. You have in the denominator, you have actually the total probability, which is usually very complicated to calculate. This we don't need here. So we can sample from, let's say, an unscaled density function. That's for example, this we do by rejection, or whatever it's called. You don't need, it makes it numerically feasible. I can't go back to this one. When we had this at the very beginning. Usually even using Bayes, this one to calculate, as you see, it's an integral. That's the unconditional density of your data. That's very complex. That's why you just sample from this one, because this doesn't depend on the parameter. And you just want to have, so it's unscaled density, which we use for producing the new states, the posterior distribution. And this is indicated by this proportional sign. Okay. Okay. Once given this, we have to do these all this conditional distribution according to Bayes' theorem, and we get the posterior distribution. And here you see, just to indicate what's to some extent new here, if you have to collect, because you want to have something for state J, you just collect all time points, but it's written in continuous time, you have just xk, where you observe the state J and then you take conditional distributions there. Okay. That's the geometric Levy. I just want to present the second process we are looking at. That's the one with the mean reversion. That's for interest rates. And so you have also here a closed form density here. You have also a kind of a convolution semigroup, which makes you easily to add up the steps over different time points. Here you see it's all normal distributed. It can be solved explicitly. We also have, as before, you have a transition density. Of course, this drift doesn't make it non-stationary. It's not a stationary process. That's a regime switching Ornstein-Uhlenbeck model. That's also a standard model used, as I said, in mathematical finance. Of course, what you finally want here, and this was actually our starting point, is to take the Heston model here, take the square root here, but this becomes so far not feasible for us, so we stick with a different type of volatility, which is not depending on the price. So in more adequate financial models, you won't also have to sigma. Also depends on the state, on the price. Not only it only depends on the state. But it's more realistic to assume that if you have high levels of prices, you have also high volatility. Okay, but nevertheless, you can run through this all as well. Just one remark to this one again. This equation, as I said, this is basically my favorite equation, which I already did in my diploma thesis, more or less, with here a square root of xt. That's the simplest non-Gaussian process. I started, when I was young, kappa and theta was the immigration rate. This was a continuous time branching process. And of course, theta itself was the long-term mean of the population. And this was the dispersion, put it like this, of the population. Just at different words, but at the same analysis. And believe me or not, nowadays, like the stochastic gradient descent, use the optimal one of this 2 billion dimensional data parameter space. You run a stochastic gradient through it, with again a Markov chain. And actually, if you think, okay, you make so many steps in order to have real steps, 1, 2, 3, 4, you'd say it's a continuous time evolution running to the minimum. And of course, all the physicists know how you connect diffusions to invariant distributions. This you can also with stochastic gradient, so the invariant distribution, which tells you the minima of your stochastic gradient descent, meaning your optimal parameters in JetGPT, can also be described by a stochastic equation, which is what's called the diffusion approximation of the stochastic gradient descent. And surprise, surprise, in some papers you also have the square root of x. Okay. So I told you I want to advertise mathematics, which you can easily apply to artificial intelligence. Okay, so of course here we had to apply to data, which we haven't done yet. But we had done a Monte Carlo simulation, a simulation study, and you see, just to give one example, the true value is 1, and actually you come to the mode of your posterior distribution after running, so our model is close to the parameters we have. Yeah? As I said, this is an ongoing project. Yeah? Now we need still a lot of computation time, and also we will fit this to data, and we have to optimize the numerics of this so far. So as I said, so the mathematics is to some extent done, and then if you like, when the work starts. So we start here in the middle, and in this case we go to data science, more or less, or to quantitative finance. I would say economics or quantitative finance. Okay. Thank you very much.
Thank you very much for a very nice talk. Do we have questions from the audience here and maybe later from the online audience? Sura, please.
Thank you very much for your talk. I'm sorry, my question is going to be a bit more general than the specifics of the talk. So, first of all, did I understand it correctly that you end up developing models, right? That maybe are adjustments of existing ones, but you end up developing new models.
Yeah.
What kind of, so I've never done research in this area, and so I'm curious, what kind of investigations lead to developing new models on the mathematical side? What is the Santa's workshop?
Okay, as I said, this was mainly motivated by quantitative finance to get better models for this. If you ask me for my own mathematical research, so what we now do, like in our joint work with Messias, is to replace Brownian motion with a more realistic noise. Like Brownian motion has this fundamental property of being Markovian and being a semi-martingale. This makes the analysis nowadays relatively easy after working 100 years on this concept. And of course, you see that you also have phenomena which are not martingales and are not Markovian. And these are, let's say, currently the mathematical challenges in the area of stochastic analysis. Like graph path theory and stuff like this, which is connected also to the stochastic equations.
And so then you try to arrive at similar results that are known for this simpler model with the replacements that you're
Yes,
saying.
you want to figure out which structures, put it like this, you still maintain by allowing your underlying phenomena to be non-Markovian and not the semi-martingale.
And this process is a generalization of the.
This one not, no.
The ones you're describing.
Yeah, yeah.
Okay, thank you. Yeah, thank you.
Yeah, thank you very much, Ludger, for an excellent talk. I just have a quick question on the parameter estimations. Have you compared your methodology or formulation with, say, Kalman filter, extended Kalman filtering, particle filter, for instance?
Yes, particle filter is was also part of this for the geometric Brownian motion. Also, particle filter was.
Okay.
We tried. I mean, the student tried. This was his task to extend this Brownian motion to apply to use particle.
Okay, and again, you see that you estimate your estimation is under the real world probability measure. Is there easy ways to transform the parameters to be able to price, say, options from your models? And now that you can able to capture this risk neutral valuation, for instance.
Yes, so of course it's an incomplete market, but you saw one of the papers with Anindya Goswami was an option pricing in this. You calibrate the minimal martingale measure. You have to choose one, and then you have the formula. Nobody so far bit calibrated, but because you have, but in principle, you could do the same approach, like getting your parameter from prices by calibration and then analysis.
Thank you.
A stupid question. You said this is a class of equation were originally, when you were a diploma student, motivated by population dynamics.
Yeah.
The generalization is from finance.
Yeah.
Now that you have the generalization, can you go back to population dynamics and do something useful there?
So I'm out of this population dynamics, but I know that like the question we were looking at this were different, yeah? But how shall I put it? Of course, you can apply this method also to population dynamics if you like, yeah? And for the estimation purpose, of course, you can do it. But from a structural point of view, it's like, how should I put it? Actually, my research I did at this time was to look at a population process like this and assume you go to the boundary at infinity. I don't know whether you know, like Martin boundary and like Schrödinger equations and so on. Yeah, you look at the Schrödinger equations of this. Yeah? Actually, the Schrödinger equations are very well connected to financial markets because you can explain it. Schrödinger equations, they have some interpretation in the space of all martingale measures which are associated with your physical measure. Yeah? Like Schrödinger, you always want to go backward. Huh? And if you go forward in infinity and you come back from infinity, how does your process look like? Huh? Yeah, and all financial markets which goes forward and has the same backward equations, and if there was only one of those, then your market is complete. And this means, so this question, actually this has nothing to do with biology. But with the equation were motivated at this time by biology, but the answers of these equations you can use in finance. Put it like this.
Thank you. Any questions from our online audience, Donovan?
We've got two.
Okay, please.
Yeah, the first one, are there areas where Markov chains apply in quantum mechanics with probability distributions?
In quantum mechanics, of course. Yeah. Like, actually, I have a bachelor thesis currently in quantum mechanics. Quantum, how it's called, quantum mechanics. So in quantum mechanics, you just, I'm now from mathematical, you place your Black-Scholes market by an Ornstein-Uhlenbeck market because the physicists they just know better Ornstein-Uhlenbeck, which is called the Langevin equation in their world. And they try to model financial markets with the Langevin equation. So if you look up what's quantum economics, sometimes it's just a different process driving the asset price.
Okay, and the second one, can the approach also be used as an alternative to the threshold autoregressive or TAR models in time series?
I mean, my general answer would be most processes in discrete time have also a version as a stochastic equation in continuous time. Like the gauge models, they have a specific volatility structure. There's also diffusive gauge models. So I actually, this specific model, I actually don't know, but for most discrete time processes, it's called what's called a diffusion approximation, which not always answers, of course, all the question in discrete time, but gives you some, as you say, stylized features also of the time series.
Okay, if there are no more urgent questions, then I would like to thank you very much on behalf of all of us.
Okay.
And give you a little magazine that NITheCS co-publishes.
Ah, very good, mathematics.
Yeah, so something to read on the flight back home.
Okay.
No, thank you very much.
Okay,
For the
thank
great
you very
talk.
much.
Thank you. And